All right, so let's walk through an example that'll highlight some of the connections between binary classification and the decision-making stuff that we've been learned, the ideas around, row-wise rates and column-wise rates. How does that stuff apply when we're thinking about classification instead of hypothesis testing? Okay, so I have a notebook, I have all my setup stuff. I have this useful function that makes a 2x2 table. You give it an array of reality, which is a bunch of zeros and ones, decisions, an array of zeros and ones, and it gives you back a nice little 2x2 table like the ones we've been looking at. Okay, so we have our data set that we're loading. This is a scikit-learn kind of publicly available data set of data on patients who potentially have breast cancer. We have a bunch of manually labeled features from imaging labeled by an expert. And so, labeled by a bunch of different experts. And we have all these different things computed based on, the things the experts label. So we have like the mean radius of, certain features of the image and so on and so on. So we can see there's a lot of different features here that we have about the images. And we also have Y, which is an array of zeros and ones saying, does this patient have breast cancer, yes or no? Okay, so we have our X, we have our Y, and our goal, remember, in classification is to say, can we use X to predict Y? Right? Can we use all of this information about the image, all this stuff that's labeled from the image to predict whether or not a new patient is going to have cancer? And so we have all these, previous patients, all the data for them, and we have our output, and we're going to learn a model that can make this prediction on new data. And so, we do the usual thing of splitting the data set into training and test sets. Again, we'll talk a little bit more about like why and how we do that and like recap that a little later in the class. But for now, we have these data sets, the X-train, X-test, Y-train, Y-test, and we're going to use logistic regression. So we put a logistic regression model, we fit it on the training set, and then we make predictions on the test set. And so we get out what I'm calling Y-hat test, which is an array of zeros and ones, right? So this is saying the first test set patient, the model predicts they do have cancer. The second one, model predicts they don't, and so on and so on and so on. Okay, and now we can compare these to reality, and we get this 2x2 table here, right? So this is, again, the table, kind of the 2x2 table we're very familiar with. Here, what is the decision? The decision says the model thinks, yes, I think this patient has breast cancer. No, I think they do. Similarly, reality is, do they actually or do they not, right? So reality 1 means they do have it. Reality equals 0 means they do. So we have this 2x2 table, and let's quickly recap, what's the false positive rate and the false discovery rate for these predictions. So take a sec and see if you can, write out expressions for what they'd be. So what's the false positive rate? Well, false positive rate is the row-wise rate. It's looking at false positives. False positives are these where we make a decision of 1 positive and we're wrong. It's false. So it's looking at this, and it's a row-wise rate based on this quantity. So essentially it's saying, the numerator is 32. We're saying, how often do we get it wrong out of the row where reality is 0? So out of patients who don't have cancer, how often do we predict that they do? So this is our false positive rate, 44%. Not great, right? Close to half. What is our false discovery rate? False discovery rate, again, that's column-wise. It says, looking at our discoveries, cases where d equals 1, cases where we predict this patient does have cancer, then how often do we get it wrong? Well, there's, again, 32 of those false positives, and we made 32 plus 99 discoveries. And so our false discovery rate is 24%. What about our true positive rate? Well, the true positive rate says, how well do we do in the bottom row? In other words, how well do we do on cancer patients? And there we can say it's, 99 of them, we get it right. And total, there's 99 plus 16. Okay, so we can see that our true positive rate is 86%, which means that for patients who do have it, we're right 86% of the time. Our false positive rate says for patients who don't have it, we're wrong 44% of the time, or we're right 56% of the time, right? So we're not doing that well on patients who don't. We're doing okay, pretty well on patients who do. But let's suppose, you go out, you build this model, you show it to a doctor, and the doctor says, well, I really want to make sure that I'm able to catch all of the cancer patients. I want to make sure that, anybody who has cancer where reality equals 1, I can catch it and I can start treatment early so they have a better prognosis. And, if that means some more false positives, that's okay. We can order more tests or figure out something, but I really just don't want to miss anybody who has reality equals 1. So how do I go about doing that? Well, maybe I can play around with the model or something, or figure out some way to increase my true positive rate, even if that potentially means trading off and making more false positives. In other words, can I do better for this case, even if it means potentially doing worse in this case? So, I use this predict method here, which gives us back the binary answer 0, 1. But the output of logistic regression is really a probability, right? It's a number between 0 and 1, right? It's like how it kind of measures like the logistic function of how close we are to that boundary. And so if the output of logistic regression is a probability, then we can instead use this predict proba method that gives us back probability. So this says, for the first patient, the model predicts a 59%. Second patient, the model predicts a 34%. So, and when we call predict, it basically just says threshold is at 0.5. But what if we were to use a different threshold? So if we want to do better than 86% on patients who have cancer, then should the threshold be lower or higher than 0.5? So I've been, working with this for a long time, and even for me, this always takes me a second. It's lower, higher, which one is which? So let's make sure we think through it carefully. So let's suppose we set a higher threshold. So we have this cell that, we set a threshold, we take the predicted probabilities, see if they're greater than the threshold, and then make a 2x2 table. So this is the one we had before with, oops, I gotta try this. This is the cell we had before. And let's run this again with a lower threshold. I don't know, let's say 0.2. So now, what happened when I set the threshold super low to 0.2? Well, what happened was, in the reality equals 1 case, now I'm right 112 out of 115 times. So I did even better than before in this case, in the case of patients who actually have cancer. But for this case over here, I did much worse, right? In the reality equals 0 case, you can see that before I was, before I was right 41 times out of like 70 something. Now I'm only right 9 times. So I set a really low threshold, and that means I, do a much better job, because even if the probability is like 0.3 or 0.21, I'm still going to declare a decision of 1, right? So even if the probability is really low, if I set my threshold low, then anybody with even a low probability is going to get a decision of 1. So we can see that if we had set a really high threshold, like 0.8, then we have the exact opposite case, where we do really well over here in reality equals 0, but pretty badly over here in reality equals 1. So again, let's try to like visualize that using a script plot. So this is the same kind of plot we looked at with p-values, except now these numbers are not p-values. These numbers are predicted probabilities, right? They're the predicted probability of being in the like 1 class. And so, with p-values, we kind of interpreted them as like, well, really small values kind of favor the alternative, big values favor the null. Here, it's exactly the opposite, right? Because the probability says, what's the probability we're in case 1, right? So we need to say, well, bigger values here mean more likely to be in class 1, smaller values mean more likely to be in class 0. So we can see that, the probabilities here are pretty spread out, for the patients who don't have it, and for the patients who do, we can see that the probabilities are kind of spread out, but they're like mostly in this, I don't know, like 0.65 to 0.8 range, right? So what we can do is we can draw a threshold, just like we did before. And I have this threshold of 0.05. And if we set the threshold to 0.05, then we can see that, well, in these, anybody below the threshold, we're going to declare a decision of 0. So in these cases, we do the right thing. And above the threshold, we declare decision 1. We make the right choice here. Well, we make the wrong choice. And here also we make the wrong choice, right? So again, we don't want to necessarily just limit our decisions this way. So we can say that these are the true positives, and these are the false positives, and so on, right? So we can see that these 4 sections actually correspond directly to our 2x2 table, right? Where these are like the true negatives, and these are the false negatives. Right, so essentially we can count how many of these points are in each of these, and we can get our 2x2 table. And so we can see as we shift the threshold to the left, then we get fewer and fewer true negatives, right? We do worse and worse in the reality equals 0 case, but we do better and better in the reality equals 1 case. So this kind of highlights the role of the threshold. Again, just like what we saw with p-values, same idea, but now in the case of binary classification. Okay, so I could say like, well, like let me try, up here I tried, like let me try a threshold of 0.2, see what I get. Maybe I could try a threshold of 0.8, see what I get. But wouldn't it be nice if we had some way of like seeing all of the thresholds at once, right? Like kind of quantifying and evaluating. Let's look at all the possible thresholds, see what we get for all of them, and visualize that all at the same time. And that's exactly what an ROC curve does. So an ROC curve, ROC stands for receiver operating characteristic. It's the name originates from like the World War II era, where they had like radar detecting like planes and ships and stuff, and would say, well, how often can we like detect that? Like the receiver, the radar receiver, how well does it detect stuff? So we have this function that I wrote that for any threshold, it computes the true positive rate and the false positive rate, essentially doing what we did in that step, right? So we can compute how many times reality is 1, how many times reality is 0. We can compute the decisions. We can get our 2x2 table. We can get how many true positives, how many false positives, and compute the TPR and SPR. And then what we can do is loop over all possible thresholds, not all possible, but loop over 100 of them. Or in this case, I guess only 10 of them. And we can get the true positive rate, the false positive rate, build those into a list, and make this into a data frame. So what does this tell us? This says, if I set my threshold to 0, then I get a true positive rate of 1 and a false positive rate of 0, right? This basically says, well, if your threshold is 0, then you're saying always make a decision of 1. So in the decision of 1 case, that looks great because you always get it right. But in the reality equals 1 case, you always get it right. But in the reality equals 0 case, you get it wrong 100% of the time. Not great. And similarly, over here on the flip side, we can have a threshold of 1, which basically corresponds to always make a decision of 0. Okay, so this is not great. This is not great. And for all these points in between, we can see that, for example, if the threshold is 0.5, the true positive rate is 0.86. And the false positive rate is 0.44, right? Exactly what we computed manually in those cells. And so we can now look at all these different thresholds, but kind of it's hard to like look at these and kind of say, oh, what's what? So that's why we use an ROC curve. So an ROC curve essentially plots the false positive rate on the x-axis and the true positive rate on the y-axis. Essentially, this x-axis is saying, how badly or how well or how badly do we do in the reality equals 0 case? The y-axis says, how well do we do in the reality equals 1 case? And so we can see that there's a trade-off, right? The ideal situation is to be all the way up here where true positive rate is 1. We're like perfect in the reality equals 1 case. And false positive rate is 0. We're also perfect in the reality equals 0 case. So this is like the best case scenario being all the way here. And generally, we want these points to be like as much as possible, kind of like up and to the right? We want them to like be close to here. So we can see that, these points are over here. So this one corresponds to like false positive rate of 0.3. It's like not bad on the reality equals 0 case. And true positive rate is just above 0.8. So we're doing really well in the reality equals 1 case. This kind of measures the trade-off between, how well we do on reality equals 1 on the y-axis, and how well, or I guess how badly we do on the reality equals 0 case on the x-axis. So this, and we can then connect the dots and draw what's called an ROC curve. Okay, so I wrote all this code to do it, but in general, you don't have to actually write all that yourself. Scikit-learn comes with these functions, ROC curve, that and ROC AUC score that do all this for you. And I just did it with 10 thresholds. They do it with essentially many more, essentially every possible threshold. So we can see that this measures the performance of this classifier, right? So we can see that there's a point here that we do pretty well. There's a point over here where the false positive rate's really high, not so great, but our true positive rate's high. And so you can look at this and say, for your problem, where would you rather be, right? For this problem, I said, oh, the doctors came back and said, well, I want to make sure that I'm doing really well on patients who do have cancer. And so that corresponds to getting a really high true positive rate, right? So they're probably going to be interested in what's going on over here, right? And you can ask, well, okay, I can give you a true positive rate of, I don't know, this is 0.96 maybe, but you have to accept a false positive rate of 0.7. So the better your classifier, the further up and to the left this will be, the worse your classifier, the closer this will be to a diagonal line. So that's an ROC curve. And we can also talk about precision recall curve. Because remember, ROC curves essentially just look at two row-wise rates, right? And we talked about how row-wise rates aren't always the best way to evaluate things. They don't take into account the prevalence. And so it's nice to be able to say, well, when I make a decision of 1, how well do I do, right? And we talked a lot about false discovery rate as a way of quantifying them. And so a precision recall curve is a way of looking at the same trade-off, but kind of including a column-wise rate perspective in the mix. So again, I'm going to use scikit-learn's built-in precision recall curve. And I'm going to compare now the true positive rate on the x-axis, which is also known as recall. And on the y-axis, I'm going to look at precision. And precision is just, vocab for 1 minus the FDP. So I can say, well, what is the FDP? What is 1 minus that? So, FDP is like, how badly do we do when we make a decision of 1? Precision is how well do we do when we make a decision, right? Just 1 minus FDP. So we can see here that, there's still a trade-off, but for, all the way over here, there's kind of like this messiness in the curve. And this is pretty typical of a precision recall curve. We'll kind of like talk a little bit more about why later. But we can see that, there is this trade-off, right? The higher the recall you want, generally the lower the precision. So this precision recall curve, which is also commonly used, kind of captures a column-wise rate versus row-wise rate perspective. So why is it all kind of like, going up and down in this region? Well, remember that if we want a lower value of recall, right, that means lower true positive rate. What is true positive rate again? It's like the row-wise rate corresponding to the reality equals 1 column. So if that gets really low, that means we're doing badly on the reality equals 1 case, which means a lot of the times we're making a decision of 0, right? So that means if we're making a lot of decision zeros, then that means that we're making very few discoveries. So if we're making very few discoveries, that means that the denominator for this column-wise rate is very small, and so it kind of fluctuates a lot. So this is something you'll typically see in precision recall curve. As you get further to the left, the curve will get messier because the denominator for computing the precision is very small, and so it's pretty noisy. It fluctuates a lot. Okay, so you've seen precision recall curve before, you've seen ROC curve before, but hopefully this helps connect what already know about those to what we've learned about row-wise and column-wise rates.